Good afternoon. This is Distributed Systems Part 2. So this is Group 11's presentation. Baraza Michael, Kimani Peter, myself Benjamin, Tait, and then we have Ben Muhindo, and then we have Odhiambo Ryan Eric. Yeah, so we can proceed to the next slide. Yes, so I'll be introducing this. So how the handling heartbeat protocol in distributed systems. So what is the handling lightweight? What is the heartbeat protocol? Sorry. So the heartbeat mechanism is a lightweight protocol where a node sends a periodic a live signal. So these are the heartbeat messages to its peers or a monitoring system. So you can see the illustration that we have here on the slide. Server 1 is communicating with server 2, just letting it know that, hey, I'm still there, so it's still alive. So we have the core components. So core component number 1 is the sender. So in this case, server 1 is the sender, which is now sending the heartbeat message to server 2. We have the receiver, which is now server 2, which is receiving, and it is expecting and it also monitors the heartbeats. So those messages of I am alive. Number 3 is the interval. So the interval is the duration between the heartbeat messages. So between every 1 to 5 seconds. And then number 4, we have the timeout. So the maximum time a node can wait for a heartbeat before considering the sender to have failed. So in the case that server 2 waits for a very long time, maybe we have a timeout of maybe 10 to 20 seconds. So when it gets to 20 seconds, server 2 considers that server 1 is now failed and is not working. Yeah, we can proceed to the next slide. So how it works, so how this works, we have node A sends to a heartbeat to node B every 2 seconds. In this case, the heartbeat is now the message I am alive. So that message showing that it is still working. So node B records the last time it received the heartbeat from A. If node B does not receive a heartbeat within the predefined timeout, it assumes that the node A has failed or is unreachable. So if the timeout was 20 seconds, as we had said, and then it does not receive a timeout within that, a heartbeat message within that time, it considers that the node is unreachable or has failed. So example, in practice, we have a zookeeper. Followers send heartbeats to the leader to confirm their ability. Then Kubernetes nodes send heartbeats to the control plane. If a heartbeat is missed, the node is marked not ready and the workloads will be moved. Yeah, so we can proceed to the next slide. So benefits of this, number 1, it enables fast detection of node failures in the sense that so the server, we can always detect which server is functioning or not, which server has failed and which one has not, in the sense that the server does not send the heartbeat message within the specified time of T, then we consider that server as failed, so we'll be able to detect a failure. Number 2, it allows automatic recovery through a failover. So in the case that we don't have those heartbeat messages within that specified time, then another server, which now is the backup, can pick up immediately. Then number 3, it can keep the distributed system responsive and reliable. So in this case, now through everything we can now have, we ensure through everything that we've talked about right now, we have reliability and responsiveness, in the sense that now our distributed system is very reliable, and now there is no failed servers in our system. So we have an illustration here. So between a client and a server, in which there's a timeout of 5 seconds. 5 seconds, and then now at the end we also have at the end now the red circle. Yeah, after 10 seconds, of course, now our heartbeat was 5 seconds. So after 10 seconds and there's no response, of course, now we have a failed server. Yes, we can proceed to the next slide. So handling heartbeat signal failures and timeouts. So in distributed systems, heartbeat failures occur when one node does not receive a signal from another node within the expected time frame, and we have already mentioned this. So this is very important in detecting crashes or unreachable components. So how do we handle now in the case that now we don't have servers that have received their heartbeats that within the specified timeout? So timeout detection. So each node expects a heartbeat within a specified window. If a heartbeat is not received before timeout, the sender is suspected to have failed. So you see, in this case, how can we detect this? How can we detect that a server has failed? Number 1 is timeout detection. So if a server was to send a heartbeat at every 10 seconds, and now they don't receive that heartbeat, now we can know that that server is considered to have failed. An example is a leader sends heartbeats every 2 seconds. If a follower does not receive one within 5 seconds, it flags the leader as failed. Okay, next slide. Okay, very well. So number two, we will proceed to failures aspect list. In this case, failure detectors. So remember in this case that we have two nodes, a sender and a receiver. And as a receiver is always expecting a heartbeat message from a sender. So in the case that we don't have that heartbeat message, we consider that node to have failed. So we have a list of um, all the suspected failures, all the suspected failed nodes. And then these nodes, since we have them in a list now, so the list now is used to initiate actions like a leader re-election, in the sense that now we need to get other nodes. We need to get other nodes that can replace the failed nodes. Number three is redundancy and acknowledgement. So nodes can send acknowledgements upon receiving heartbeats, and then redundant channels, e.g., TCP and UDP, help reduce positives. So once a node receives the heartbeat message, it can also send an acknowledgement, and this will also help to tell now the sender that the receiver is also working. Then number four is gossip protocols. Then nodes share their view of which nodes are alive. This improves the accuracy in very large scale systems. So monitoring all of the nodes in a very large scale system is very difficult. So we can have nodes sharing their view in which nodes are alive. Okay, we can proceed to the next slide. Adaptive timeouts. So in adaptive timeouts, intervals adjust dynamically based on network conditions. Remember that for server A and server B to communicate, now the sender and the receiver, it all depends on the networks. So in the cases that we have very, very high and very good network connectivity, we can have the timeout to be a very small period of time. But in the case that now we have very poor network, we can increase the timeout so that we don't have the sum of the nodes to be considered to be failed. But in the real sense, it's only the network that is a problem. So that adjusting the time intervals based on the network is also very important. Number six is also reconnection and retry mechanisms. So systems may retry the communication before finalizing that a node is down. So we've spoken that some of the times the problem might be the network. So we can now retry communication before now coming to the conclusion that this node completely failed. So key challenge is false positive. So because of these other factors that keep on changing like network, we can have nodes that are considered to have failed, but in the real sense they are still working. So we can ensure that these nodes are also
Hello, Benjamin, are you on? Okay, Peter, you can hear me, yeah?
Yes, I can.
Benjamin, you're lost. Have you forgotten content? Are you blank? It is part of life, man. Endure. Or I should start. Benjamin, you're looking at us, but you're not responding, man. Oh, you're frozen. You guys are delaying my sleep, man.
How? Now you'll have to go through this small video. You have to cut this one again.
Yes.
You can start where he has stopped.
sorry
So,
guys.
Benjamin, you had gotten lost. Have you done?
Yeah, my bundles had expired. Now,
Hamia Kafoka. Kafoka is the Siri.
sorry guys, can you now hear me?
Yes, we can.
Okay,
Yes,
let
we
me.
can.
Sorry, my network had disconnected. Also now the power has also come back, so it's a good thing.
Oh, there's power.
It has now come back.
Now I can go home.
Yes. So let us proceed to the next slide.
3, 2, 1, go.
Yes, so we can proceed. So why election algorithms and assumptions? So this part I will let Michael to continue and take us through this part. So thank you very much.
All right, so I'll be taking you through the electoral algorithms and the assumptions. So basically, we know that in systems there is always a leader or a coordinator. So these election algorithms are used to select one node as a leader or coordinator to manage tasks such as synchronization, mutual exclusion, and communication control. So as we learned in class, we learned that there must be at least there must be one leader, yeah. So and that's why we must have an election algorithm. Now, but to look at it deeper, we have to look at some points. So for instance, why should there be election algorithms? Number one, that in a distributed system there must be one leader, yeah. So there must be one leader who is able to coordinate everything. And also, if that leader fails, a new leader must be selected to ensure continued coordination. So, because otherwise there will be problems when it comes to synchronization, yeah. There will be problems when it comes to communication control. So there must always be a leader. Once a leader fails, then a new leader must be selected. Then we have election algorithms provide a systematic method to perform this selection. So it doesn't become an ad hoc process. So not anyone becomes a leader, yeah. So the election algorithms make it so that there must be like some protocol or some set of rules that now determine why this one is a leader and why the rest are not leaders. Yes. Now, there must be some assumptions when it comes to election algorithms. Yeah. So this one of those assumptions is that each node has a unique identifier. Why is this paramount? So that we know that node A is the one which has become a leader and not node B. Yeah, so there must be a unique node identifier. The other thing is there must be communication between nodes via message passing, yeah. So because it's an election after all, then the system can detect node or coordinator failures. Why is this important? So that we are able to know that the leader is no longer has failed, yeah. So we're able to detect that, and we're able to detect that, oh, so these are the leaders that are there, and these are these are the nodes that are now active, and these are the ones which are not active. This one is responding, these ones are not responding. Then the other one is any node can initiate an election, yeah. So that's one of the another assumption. Then the other one is there must always be one and only one leader active. Now, if we had 5 leaders, then there will be a problem of synchronization after all, yeah, which we are trying to curb. So by having one and only one leader, then it becomes easier for us to synchronize and be able to facilitate communication easily, yeah. So there is no problem when it comes to this node leader node A is saying this and leader node B is saying this. So with only one leader, it is easier. Now, what are some of we have the Bully algorithm. So this is a well-known algorithm for electing a leader in distributed system. Now, how does it work? So we have a node that detects the coordinator has failed, which initiates an election. So we have remember we say that one of the assumptions is that any node can initiate an election. So here we must have, number one, a node that detects the coordinator has failed. The coordinator basically is the leader. And then what does it do? It initiates an election. Then it does what? It sends an election message to all nodes with higher IDs. Yeah. Then if no node responds, it declares itself the new coordinator. Yeah, so let's say it sends the nodes and then no other node responds, it declares itself the new coordinator or the new leader and sends a coordinator message to all lower ID nodes. So remember, the high ID nodes is where we send the election message. No response, then we send coordinator message to all lower ID nodes. Remember, all nodes must have an ID. And then if one or more higher nodes ID responds with okay, they take over the election. Yeah, so this is option number 2. So option number 1 is when we see that no node responds, so it declares itself. Option number 2 is one of the higher nodes or more respond with okay, they take over the election. Eventually, the node with the highest ID becomes the new coordinator. So yeah, that's basically it when it comes to the Bully algorithm, and you can see why it's called the Bully algorithm. Now, what are the advantages? It is a deterministic result because basically the node with the highest ID wins. If nobody responds from up, then I'll be the one with the highest ID by then, as in who has responded, so I win. And number 2, it is easy to implement because you can see we only have 2 conditions. So number 1, you see that it has failed, there is no leader. Okay, the leader has not responded, so you initiate an election, you send to the higher ones. If no one responds, you become the new leader, you tell the lower ones. If the one upper responds, the one with the highest ID responds, so it becomes the leader. So it's very straightforward. What are the disadvantages? High message overhead in the system. So you can see you can see that that's the complexity. It has a very high complexity. What if you have 1,000? What if you have 1,000 nodes? What if you have 1,000,000 nodes? This becomes very complex. And number two, it assumes nodes know all other node IDs. Yes, this is also one of the assumptions. Now the diagram beside there just shows the process, and it's just the same thing that I've said. Next slide. Now, the other thing is the ring algorithm, and it looks at the worst case scenario. So basically, it uses a logical ring. Yes, not a physical one, of course. A logical ring where nodes only know the immediate successor. Yeah. So unlike the first one, which assumes that you have to know all the others, this one knows only the immediate successor. So how does it work? As usual, a node detects coordinator failure or the leader failure. It starts an election by sending an election message with its ID to its neighbor. So in this case, doesn't have to know all the others up there or down there, just need to know the neighbor. Then each node forwards the message around the ring, replacing the ID if its own ID is higher. So let's say I send it to my neighbor who has a low ID, then it will not be replaced. Yeah, it does not replace with its own, it will just pass mine. But if we have the ID, if I pass to my neighbor and has a higher ID, it will replace my ID with its own before it passes. Yeah. So each node forwards the message around the ring, replacing the ID if its own ID is higher. When the message returns to the initiator, it knows the highest ID. You can see how efficient it becomes, because at the end of the day, you'll be having a higher ID. Then the initiator sends a coordinator message with the highest ID around the ring. Actually, this is very straightforward, as you can see. Next. Next, please. Now let's look, how does this worst scenario come in? If the node with the lowest ID starts the election message must pass through all nodes messages twice. Yeah, so you can see that. So what are the advantages? It has fewer messages than the Boolean algorithm. Now remember, in the Boolean algorithm, you had to know all the higher. Okay, somewhat you had to know all the higher and all the lower. Yeah, but in this case, you don't have to do so. You just need to know your neighbor. As long as you know your neighbor, then you're good to go. It works even if nodes only know the immediate neighbor, yeah, just as I've said before. Disadvantages, it is very slow in large systems, yeah. So you can see the worst case scenario there. Then it also, you can see it fails if the next neighbor is down and not bypassed. Yeah, so you can see that. So for example, here you can see the election has been started by process 17. Yeah, the highest process identifier encountered so far is 24. Yeah, you can see that. Now, the final lead, of course, it will be 33 because it's the highest. Yeah. Then the worst case scenario occurs when the counterclockwise neighbor has the highest attribute. Yeah. So just as you have seen, yeah, the counterclockwise, it has the highest attribute because it must go through all of them. Next.
So consistency models in distributed systems. So consistency models define how a distributed system behaves in terms of data visibility and read and write updates across multiple nodes. So essentially, consistency models defines the rules for how updates and how read and write updates should be shared across a distributed system. So we have two types of consistency models, where we have linearizability, also known as atomic consistency. So this one gives the illusion that all operations happen instantly and one after the other. So this makes the system behave like a single point, a single system. So what it ensures is operations appear to take effect instantly at some point between the invocation and the response. It also ensures that the system preserves the real-time ordering of operations. It also, so every read returns the result of the latest completed write. So an example is, let's say we had a shared variable x where process A performs write and it defines x as is equals to 5 at time 1. Then process B performs the same process B now reads what is written in X at time 2. So this implies that time 2 comes after time 1. So this principle, linearizability, guarantees that B reads the updated value, which is 5. So real world examples are such as Google Spanner and Apache Zookeeper. As for sequential consistency, operations appear to be in some sequential order, yani meaning one after the other. So it ensures that operations are executed in some sequential order, just as I've said. The order of operations from each individual process is preserved. And lastly, real-time ordering is not necessary, as opposed to what we discussed lastly. So the key difference between sequential and linearizability is that it does not guarantee the actual real-time sequence is preserved, and also it focuses on logical consistency rather than real time. So, for example, if P1 writes x is equals to 1 and process 2 writes x is equals to 2, we can still deduce that P1 and P2 will still read different values of x, but it's still acceptable in that as long as a consistent order is maintained, we can differentiate which is for process 1 and which is for process 2. So a real world use case of this would be maybe shared memory systems and cache coherence protocols. So the difference between linearizability and sequential consistency can be summarized in this table. So linearizability has real-time ordering, as for sequential it does not. Linearizability has global operation order, which they both happen to happen in both consistencies, since they are both logical. They use logical order. So as for performance, the linearizability is slower. This is because it needs coordination to work, and for sequential, it is relatively faster. So use cases for linearizability are such as banking, coordination, and even leader election. As for sequential, it's shared memory and cache systems. So for the next discussion will be on distributed mutual exclusion. So a distributed system, it ensures that only one process at a time is accessing a critical section. So there's no since only one process at a time can access the critical section or the resource, the it does not allow for shared memory, or there's no global clock to tell who was first to try and reach the resource. So we have a couple of distributed mutual exclusion algorithms, such as this Ricat-Agrawala algorithm, where it is a permission-based system where a process sends a request message to all other processes, and others reply with okay if they're not using the process, if they're not using the resource, or their request has a later timestamp. If all the processes say okay, it enters the critical section. The key features in this include the Lamport timestamp, which essentially is used to order requests logically so that we can know who came first. Excuse me. We also have the messages that are used. We have the complexity that 2 open the brackets n minus 1 messages are used in total. So one request and one OK per each of the processes. And lastly, there is no central coordinator. Therefore, it is decentralized. As for the advantages, we can see that it is fair since all requests are honored, and there is also no starvation since every process gets a turn. Lastly, since it is decentralized, there is no single point of failure. As for the disadvantages, we have high message overhead. As we have seen, the each process has in complexity has the message complexity as described in the key points. And lastly, all processes should be online. So they have to be online so that we can see that they are responsive. And if one is slow, this means others will be delayed. Secondly, we have the token ring algorithm. This is just similar to what Michael has talked about, where all the processes are arranged in a logical ring, and each process knows who is next to it in the ring. So a token is passed around the ring, which only the holder of the token can use the critical section or the resource. So after finishing its task, the process passes the token to the next process in the ring, and it goes on like that. So as for the points, the features, there's only one message per entry. Therefore, does not have uh, a high message complexity, and there is no need to request access since you just have to wait your turn. So the pros include it's simple and fair since every process gets a turn as it goes round, and also, just as I've said, the low message complexity. This is very efficient. And lastly, as for the cons of this token ring algorithm, there might be token loss. Just as Michael said, if there is a crash or a network failure at one node, it must be detected and regenerated. So this may add into the complexity. We also have the fact that it is slow in large systems since it works around going around a ring. Many nodes can end up waiting if the system is large. Lastly, we have the centralized mutual exclusion. This is where we have a central node, otherwise known as a coordinator. So each node sends a request to the coordinator, and the coordinator grants access if the request is free, if the resource is free. So after the use, the node sends a release to the coordinator to notify them that they are no longer using the resource. So the advantages of the centralized algorithm is that it is simple, and since it is easy to understand and implement, and also there are only three messages: the request that the node sends, the grant that the coordinator acknowledges, and lastly the release from the node. So we have also mentioned that it is easy to implement and to understand. As for the disadvantages, since it is centralized, there is a single point of failure. So if the coordinator crashes, the entire system will in turn crash as well. There is also the bottleneck at the coordinator, where the coordinator may become overloaded with too many requests. Therefore, this will end up slowing down the performance of the coordinator. So in this diagram, we have two processes which want to enter the same critical region at the same moment. So process 0, since it has the lowest timestamp, it wins. So we can see when process 0 is done, it sends an OK also. So 2 can now enter the critical region. Thank you. I will now pass it on
To
to my
begin,
colleague to
let us
continue on
understand
with
what data
data
replication means in a
replication.
distributed system. Data replication involves creating and maintaining multiple copies of the same data across different nodes or servers in a distributed system. The server might be located within the same data center or across the world. So in the diagram on the right side, you can see a central master node connected to several replica node that is copied from the master to the replica to ensure that multiple copies of the data exist in simultaneously. So this is important because if one node fails due to hardware failure, network issues, or power loss, user can still access the replicated data from another node. This greatly improves the system's reliability and performance. The purpose. We have the data replication improve data availability. This means users can always access data even if some of the servers fail. It ensures fault tolerance. The system can continue operating without data loss during failures. It enhances read performance in systems where many users, let's say where many users only need to read data. Replicas help distribute the load, speeding up responses. It can support disaster recovery. So in case of catastrophic failure at one location, data stored elsewhere prevent total data loss. Next slide. Next slide. Oh no, go back. Yeah, there. I will discuss two types of data replication strategies used in distributed system. So the first one is synchronous replication, or how it works. The primary node master write data to its local copy and simultaneously initiate writes to all replica node. So the write operation completes only after all replicas acknowledge receipt. This process guarantees that all replicas always have the exact key data. The key characteristics are it ensures all replicas are consistent with the master, guarantees no data is lost if the primary fails. Use case example. Let's say in a banking system, consistency is absolutely critical. For example, when you withdraw cash from an ATM or perform a card transaction, the bank must ensure your account balance is updated in real time across all servers. If servers disagree or lose data, it might result in duplicate withdrawals or incorrect balances. Therefore, banks use synchronous replication to guarantee real-time consistency of financial data. Let's move to the next slide. In the diagram, you will notice how the arrows between the master and the replicas represent simultaneous writes. You will also note how the client waits for a confirmation, assuring that all replicas are updated before the operation completes. If even one replica is slow or unresponsive, the entire operation is delayed as the master waits for every replica to respond. About the pros, we have the strong consistency. All replicas always have the latest data. We have reliable data durability. Even if the master fails, replicas contain the latest data. The cons, slow write, because the system must wait for all replicas to acknowledge every write. And the last cons, we have a single slow or failed replica can block all operations. Next slide. Now let us discuss the second one, which is asynchronous replications. How it works. So the primary node writes its own data store. It returns a success response to the client before propagating the update to replicas. The key characteristic, we have the replicas may lag behind the master, faster write and higher through outputs. The use case example, we can consider social media platform like Facebook or Instagram. When you post a comment or like, the platform prioritizes speed over strict consistency. If the data takes a few seconds to reach all replicas, data is acceptable. And this is why asynchronous replications is used to handle millions of user actions quickly without blocking the system. Yeah. Um, about the pros, higher availability and responsiveness. If some replica fail, the system still process writes. So it's also support offline write and eventual synchronization. Client does not wait for the replicas. The cons, temporary inconsistency. Replicas might have all data for a while. Uh, we have data loss risk if primary fails before synchronization. If the master crashes before synchronization, replicas recent write could be wrote. So let me talk about the diagram on the left. So the client receives a success response immediately after the master update itself without waiting for the replicas. Background updates occur later. So for this one, comparing to the synchronization, for this one does not wait for all the replicas to have the latest update, but after it updates itself, just directly send feedback to the client. In the next slide. So replication architectures. We have the master slave. One master handles write, slaves, replicate, and serve reads. We have the master. All nodes can write. Coordination need to resolve conflict. We have peer-to-peer. All replicas are equal, suitable for fully decentralized systems. Next. Benefit of replications. We have high availability, access data, even some node fail. We have fault tolerance, continue operating despite failures, load balancing, distribute read queries. We have geographic distribution, serve user close to their location. Now the challenges about these data replications are assuring consistency across nodes is difficult, conflict resolution in multi-master setups. We have managing replica lag and network partitions. So I will now talk about the real-world example. We have Google Spanner uses synchronous global replication to ensure consistency across continents. We have MongoDB uses replica sets with automatic failover, typically asynchronous replication. We have Cassandra implements eventual consistency with tunable quorums for read and write, balancing consistency and availability based on needs. So in conclusion, data replication is vital for ensuring reliability, performance, and fault tolerance in distributed systems. So choosing between synchronous or asynchronous replication depend on the system priorities. If you need if you need strict accuracy, like in banking, synchronous application is preferred. If you need high speed can can tolerate some inconsistency, and asynchronous application is either. Thank you for listening.
So I'll take you through the applications of distributed database systems. So first we need to understand what a distributed database system is. So a distributed database system is used to store and manage data across multiple nodes or locations while appearing to users as a single unified system. So they provide key advantages such as scalability, fault tolerance, and high availability, which are critical in many real-world applications. So on the diagram on the right, you can see a visual representation of a distributed database system, which are all connected through the internet, and we can see how they are distributed across it. So some key applications of distributed database systems. One, we have cloud computing and global web applications. So some examples, we have Google Spanner, we have Amazon Aurora, and Microsoft Cosmos database. So why are they used? So they serve global users with low latency. They also support scalable storage and computing power, and it also enables 24/7 availability across the time zones. So some key uses of cloud computing. Uh, One is for geographic replication of data. So the data is distributed across various regions. We also have auto sharding for scalability, in that these systems can be able to scale over large areas. And we also have fault-tolerant transactions, in which when one uh, area of the cloud fails, it doesn't affect all the other areas as well. So next slide. So we have the second application, which is e-commerce and financial systems. So some examples, we have Amazon, we have PayPal, we have Alibaba and Stripe. So these systems, they use distributed databases to process millions of transactions with accuracy and consistency. So these systems must ensure that that there are no duplicate transactions or data is lost. So some key features of e-commerce systems. One, there's strong consistency with the ACID properties, which is atomicity, consistency, independence, and durability. They also have a high throughput, and they also have a rapid failover. And as well, they also have high disaster recovery mechanisms as well. So next slide. The next area, we have telecommunication networks. So some examples, we have many mobile service providers and internet routing and DNS databases. They use this. There are some examples of telecommunication networks. So these distributed databases, they store subscriber profiles, billing records, and routing information for mobile service providers and internet service providers. So some key features of telecommunication networks, there's real-time synchronization across regions. In this way, all the databases are kept consistent across all these regions in which they're stored. There's also partitioning for faster lookups, which reduces the time needed to find these records that are stored there. And there's also high availability for uninterrupted services, as these services need to be available when they are needed. So the fourth application, we have healthcare and medical records. So some examples, we have the NHIS, which is the National Health Information System, and we also have the distributed EHR platforms, which are electronic health records. So these systems, they use distributed databases to store and share patient records. So some benefits of this, there's reliable access across hospitals and clinics, in which all these, they are able to access all the data about for that the patients of that are stored, the data that of the patients that are stored across all those different hospitals and clinics. The second, we have encrypted and backup for medical data. So this enables the security aspect to be preserved in that this data is not able to land in the wrong hands. And thirdly, there's the high fault tolerance to avoid downtime. So the fifth application, we have scientific research and big data analytics. Some examples, we have the CERN, and we have NASA, and we also have weather forecasting systems. So these areas, they use distributed databases for simulations and experiments. So some key advantages of this, we have parallel query processing, which enables faster processing of data. We have distributed storage and computation. For example, we have MapReduce, and we also have metadata synchronization, in that data is kept consistent across all the various platforms. And the last application, we have social media and streaming platforms. So some examples, we have Facebook, Twitter, YouTube, and Netflix. So these organizations, they store massive amounts of content, and as well as user profiles and activity logs. Some key uses are consistency, for instance, in the cases of likes, comments, and views. There's load balancing through horizontal scaling, which enables the databases to not be overwhelmed, and we also have fast content delivery via caching and replication, which increase the computer processing speed. So some key benefits of using the distributed databases, we've seen we have scalability, which enables more nodes to be added so that you can handle growing data. So this data can be hosted in those nodes. Second, we have availability, in that the system remains operational even if some nodes fail. Thirdly, we have localization, in which the users are served through the nearest servers that are near their locations. Fourthly, we have fault tolerance, which enables recovery from crashes without data loss. And lastly, we have high performance, in which queries can be run in parallel across various nodes. So that concludes our presentation, and thank you for listening.